which encapsulates, I believe, virtually every or a very large set of problems that we have in the world can be iconized like that. That star essentially says that that's my best estimate, and this is now is transformed from D minus D yesterday. It talked about generalizing work to base work. And we've been hearing about basic words all these days, so I don't have to tell you what it actually means, but essentially that make use of all the information, all the knowledge you have, and also the other. So there's a prior knowledge of the model, which is of a normal Gaussian distribution, and also of the new data that comes. And then we seek an A equals periodic model, given dm equal to 2, we maximize this probability. And Professor CBI explained on the very first day why the personality. So I shan't that. So that is what maximizes. And because there's a negative, so this is, as you see, that's that part, and then some a priori information about the model. Over there. So that's what I have written down over here. And it's the product of those. Of course, the exponents will sum up. There's a negative sign, so if we maximize that, we have to minimize the actual quantities, which are over here. And that I minimize with respect to some model R, which I believe is my best model. And it will maximize that probability. So I do it in very much the same manner that I did yesterday, that D will survive when Q is equal to R, and then that translates itself into this kind of an expression, and finally I get this. So that's my model, and if I transport it on the other side, then of course I have my so that's what N is going to look like, and the model is going to be given by this. So this is the Bayes inverse, D minus dt, and D minus d is that quantity multiplied by that quantity. And you can compare it with what I obtained yesterday for the when I minimize the data resolution, or which is the same thing that I averred without proving. It's also the least square inverse in this quantity. So we can see this covariance, which is that quantity of covariance of data that transport.
So when you don't have data, in your situation, when you start out, you don't have data with you, because if I understand correctly, you are trying to come up with what's the best sampling strategy. So then how will you get
how do I get that?
Get the data related quantities, C sub B and so forth?
Oh, I wouldn't get that until I have data.
Yes.
Because C sub D really comes from the data. That gives you the knowledge about the data.
Yeah.
So that I have to have eventually in order to get the model. I can't get the model without the data. I can get the G without the data. Also given certain conditions. In this case, I'm applying the Bayes rule. In the previous cases, I used another strategy. And there are a number of other strategies, Moore-Fedroy inverse, many other kinds of inverse cases, depending on what kind of a strategy you adopt. The least squares is one, minimum norm is another. You can mix them up. You can also mix covariances to be minimized. So there are several possibilities that could happen, but of course you wouldn't get the model until you have the data, because that comes from here, right? So And so this is what I get, and that's my model. And this is the covariance of the model. So if you know the model, the covariance, the model is easily obtained, the usual rule. And it turns out to be the same as A, which is this. And this I wrote down just to recall and connect it with this square inverse. So that's as far as the Bayesian inverse is concerned. I come down to Kalman filters now. I'm not very sure as to whether Kalman was aware of the, well, he must have been aware, but, and probably he had at the back of his mind the Bayesian rules and rules of inference. But essentially what he said that I have two pieces of data. This could be, for example, the length of a ruler, which I obtain at two different times, or I could obtain them from two different instrument systems. And how do I make the best use of both these pieces of information to get better estimate? So he argued that I want to fuse this because as far as Kalman filter is concerned, and of course these are linear systems. So linear superposition is possible since it's a linear system. But what is the logic of this system? So there are two possible answers and possibly more. One is that you combine the first set, whose expectation value is x1 dash and variance is sigma 1, and the other data set is this one. We combine them in such a way to obtain x star, so that x star has a minimum variance. The variance of x star is this. So combine it with these weights, w and 1 minus w. So you can see that you can write the variance of x star which is being solved as this, and then you minimize that. You get with respect to w, and if you combine them to the maximum, or the second approach could be that we combine both of these to maximize the joint probability p of x1 and x2. So you do either of those, but the result is the same. So in some ways they must indeed be the same, although we are making two different statements. So what one gets is that the estimate x star then becomes equal to this, and I write this whole quantity over there as A, so one can write it after Kalman. You can write it like this, which actually means that this is my first estimate. It could be in time, not necessarily, or it's something which is given to me as one or two or one of several. And I just multiply k by this difference, and I get my next estimate. And similarly, covariance, all that I do is I take the previous covariance and multiply by 1 minus 2. So k has substituted all the information about what has happened before, in a sense. If we assume that we are at the nth step and there was n minus 1 and minus 2 step and so on. So k is known as the Kalman gain. And these are assimilated in it all information relating to the current estimated covariance as well as the covariance of the current measurement errors. And together with the state vector and its covariance at one previous system, it contains all the information needed to obtain the best unbiased estimate of the stable system and subsequent step.
So what is x1 prime?
Beg your pardon?
What is x1 prime?
Oh, that's the expected value of the first data set, and yeah, that's the expected value of the first.
And what is x1?
x2 minus x1. Oh,
Prime probably should not be.
yeah,
X1 prime is the observation. I don't know.
yeah. x2 is observation, and x1 I suppose should be the same as that, which I won't right. x1 is the best estimate of the previous one, which will be x1 dash. So here is an example of a boat at sea, and this boat is stationary. Consider it anchored at the moment. So that is the first data set that you get. It has some GPS and it sends that information to a friend that here I am. And at another instant, or maybe using another set of instruments. This is the other data set. These are the two data sets about the position. It could be at instant t and instant t plus delta t, but that's not necessary. It could be at the same instant obtained by two different instruments.
I'm sorry, but I'm trying to understand what is this capital N? So I understand.
Oh, the capital N only means that it's normally distributed. I beg your pardon. This
But
is,
then that says I have a normal distribution which center is x1 prime and its
And
covariance
variance
actually
is sigma.
is sigma 1. But now you have a finite sample of this, and that's your data set, or not? You have a finite sample of this multivariate Gaussian, and that's your data set.
this is the statistics of that data, that information that I
I
have.
think what Eric is asking is, have we got one number at time t, x1 prime?
No, you have a set of numbers.
It's a distribution.
You have a set of numbers and you have a distribution, right? And then with another instrument or at another step time, you do the same.
Okay, so you're saying you have a finite sample, and you characterize that by the means and covariance matrix of the sample.
Right. Thanks for making.
But if it's a GPS, for example, sigma 1 is the error in the GPS, or?
No, the board can move a little bit up and down here, so there will be some.
Yeah.
Okay.
Or even if the board is completely stationary, you have another GPS, which has another kind of statistic, because no measurement is accurate. So that's what is happening. This is the first set, and that's the second set of information. And eventually, when we merge them, the Kalman gain, you get this one. So we can move on now to a slightly more realistic situation. The board is moving, so its position at an instant time t1 is given by that, again statistics of the data, and at t2 it's given by this. And its position, of course, at time t2 can be predicted also from the knowledge that we have. So where it was at t1, which will be x1, where it was plus velocity times time difference. And similarly, the covariance of x2t can be obtained, we call it sigma squared. So we can then fuse these two data using the same Kalman argument to give us x star equal to this and covariance equal to this. So here k has become slightly different from the other one, but basically the formalism remains the same. So that's what has happened. This boat has moved over there, and at the second position, this is the predicted one, and that's the data, and finally one obtains this solid line, which is the best distribution. So we can move on to a more real-world Kalman filter, where you have data x at time step k is a vector. It could be a state of the weather, it could be a state of any system, and the present estimate of this state is this. Those are the various components of this state or various elements at the kth step, and is derived from the previous state by some kind of dynamic like this. We also have the present state also influenced by some factors which may be present at the previous step. This may not necessarily be there in all the situations, but we generalize it. So, in other words, what one is trying to say is that I can predict at the kth step, I can predict the state of the system by using its evolutionary dynamics and also some other factors which may be intervening. And of course, this is the process model which has the same zero mean and Q.
So which things are known and which things are not? Are A and B known?
Beg pardon?
Which things here are known and which things are you going to try to infer? Yeah, are A and
X,
B
K,
known?
and U will be known. The K minus 1 step.
The X's and the U's are known?
Q is known,
Q is
and
known.
A and B
Are not
is the
known.
dynamics.
Oh, but are they known or not?
Yes, they are known, like the velocity in the last case.
So it's a recursive.
So what's the difference between the star and the P there? Why are you using the superscript star?
That's the predicted one at the instant K, and this was my best estimate, sorry. XJ star was my best estimate at K minus 1. Okay, so I get my best estimate at a particular time. I move it into the future.
So this is not the equation for the actual true generative process, you're giving the equation for the update.
This is for the prediction. But I have data. And the data is here at the KF step. And the data too could be coming from an instrument. And that instrument has itself its own transfer function, which is converting, it's translating this state of the system at K to djk through some kind of a transfer function here. So the data is going to look like this. And this is what happens in the real world, because you have some kind of an instrument which are really sensing the state itself. So that is how I will write my predicted X state at the instant K, and this is the data at the instant K. So getting a little more complicated, but we then obtain the best estimate at the kth step. This star means the best estimate, using the same formalism at the Kalman filter. And if we simplify the notation, it's going to look like that. Kk is the Kalman gain at the kth step, which we have to reevaluate. And we reevaluate it by minimizing the covariance, and this covariance is equal to this. So all that is algebra. And if we do that, we differentiate its trace with respect to Kk, then we get the value of Kk equal to this. And that's the Kk at the kth step. And Dk star is my best covariance at the kth step. And S equals.
What do you mean by best covariance?
Which one?
What do you mean by best covariance?
Best covariance means that at this time, at the kth step, I got my best estimate and best covariance.
It's corresponding to the best estimate. The covariance corresponding to the best estimate.
Right. So it's something like that, and you can see that these quantities are here. So it goes on in an iterative mode. They project the state ahead, and this is the covariance which you also project ahead. So this is what we are carrying into the filter of K plus 1 step. Compute the Kalman gain by minimizing the variance, as I have shown before, and then you iterate the process from one step or from one sample of data to another sample of data to go on improving the last state. So something like this, which is very similar to what we have been seeing about said about Bayes. And I don't know whether Kalman anticipated Bayes or he simply reformulated it in a different way, but they look quite similar. And but let me move on to Kalman filter, where I had assumed that A is something which is linear. The prediction is linear. The prediction may not be linear. It could be a functional relationship, like xk1, for example. It could be a function of the xk at the last step and uk at the last step. This is the step ahead. So this could be written as something like this, and in this form.
These are all recursion forms in time.
You could say that. But right now I'm only relating k to k plus 1. Okay, and you can convert this, you can translate it into recursion form. So I've rewritten it in this form just to show that this is a function of xk, but this is xk star, which is this one that I know, and all this. So I can calculate x k plus 1, and this capital F is actually this gradient over there. I know the function. I assume that I know the function, therefore I can calculate the gradient. So that's the gradient. And we go through the whole process. And
So am I understanding correctly that the way you're dealing with non-linear update functions
yes,
is to say the
I'm linearizing
estimated
it.
ones are going to be close enough
Yeah.
so that I may linearize around.
Yeah.
Right?
So that's why you always linearize at this step k.
It's the Taylor series expansion of that nonlinearity.
Yes, but at this state k. At just the previous step. That really data, somehow it's small data. So it comes like that. And having just linearized the two operators and treating the predicted value at this step in the above observation constraint system, we now evaluate the best possible estimate. And that is what one gets. The best possible estimate is Tk plus 1 star over here. K plus 1 star. K plus 1 is given by that, and S K plus 1. Compare these values of K and S with those of the standard Kalman filter, and the standard Kalman filter H was equal to 1. And there was no functional relationship. So x1 was equal to d1, x2 was equal to d2. So this will reduce to the standard simple Kalman filter if we use those two ranges. Also recall the Bayesian inverse and the model covariance. So this is the Bayesian inverse, that's the model covariance. And the Kalman filter quantities, which is the best estimate of the covariance here and the best estimate of the state. And if you look very closely, they look quite similar. And again, one begins to wonder as to whether they are indeed different or not. And I begin to believe that they are essentially at the root, they are the same approaches. If you look hard at this, you will be able to find the correspondences. And that just shows that the Bayes rule, which was used to obtain the inverse, was there. Now, one of the main problems, one of the main strategies here is that I transport my covariance from k minus 1 step to k step. And if you're working in a million-dimensional system of the atmosphere age, then that becomes computationally virtually impossible. So one has to think of other strategies to be able to do that. And therefore, what one does is that one chooses an ensemble of states and moves the ensemble of the states and their covariance into the feature. I don't do weather forecasting myself, so but I know that this is how it is done. And this is how today's weather is transported tomorrow by the dynamics that I know and all the dynamics yesterday. And I take its covariances forward. And then I merge with the data that I obtain and the data statistics that I obtain every 6 hours or whatever. So this is the way, instead of carrying the entire covariance forward, some sample values are taken over here, carried forward, reconstitute a covariance over here, and then use it to build this data. So I'll stop here because I had an example but I couldn't convert it into a PowerPoint.
So, since we're talking about real world, if you find that consistently while making your updates, that you're systematically off, because you have an observation at every point, you have a chance to actually check the goodness of your model as well, but that's not incorporated into this framework.
What is not incorporated?
Suppose you're always predicting systematically off for the next step. Suppose your model is off by
Oh, that means your dynamics is probably not
no,
quite
so
right.
since we're talking about real world, the missile and there's a fly sitting on the
Yeah.
missile or something like that.
Yeah.
So how do you then incorporate it?
Something must be wrong. What are we doing here is that we are taking the real data and we are then taking the predicted value. So if the predicted value and the real data is coming from observation, and the purpose of the real data is to to pull my covariance, and take it to the real world situation. If it is not happening, if somehow my covariances are always falling short, then that means that some of the physics I have not been able to put in that function.
So what is a goodness of prediction score for the Kalman filter? So that you can pick up a systematic bias. Because in this case, no single step prediction will
The
show up.
covariance itself.
The covariance will tell you how good or bad you are.
In fact, the covariance will be a hyperellipsoid, right? You can think of it in two dimensions.
The covariance tells you the degree of noise in your instrument. It does not tell you about the error of the
To
model.
find a covariance of your state that you get.
But you can perturb your unobserved state variable and then use the Kalman range to update so that then the next data point.
No, but that's what is being
Yeah,
done.
yeah.
But after you have obtained the final data point, then whatever its covariance is a measure of the uncertainty that you
What
have.
will happen is that the thing will okay, so if the model is systematically wrong, and it will always be off in its prediction,
Yes.
it will interpret that as saying the noise in the update from one step to the next must be big
Yes.
because I'm off all the time.
Exactly.
And therefore it will give a big variance.
So that will give you an insight into your model, and then you go
Yeah.
back and sort of
Is
see
it-
where you're
So
linked.
that
But-
is
but- but
variation
always-
is larger than.
There's no scale. You've never told me a scale to say that this much noise means something is wrong. You've never said anything like that here. So I can never.
Oh, these is already normalized.
No, I understand. So that's why, unless you're. So again, I'm coming back to this point that you cannot distinguish between errors in instruments and errors in the model because you've not told me a natural
Well,
scale.
it's saying that they are normalized in some way.
In the Bayesian equivalent, you have the observation equation as what is known as an observation variance, and your system evolution equation as what is known as the system evolution variance. And if you fix the observation variance based on previous knowledge or some data from the past, then your system evolution variance will often be set as a fraction of that. So which is basically your signal to noise ratio.
No, the system evolution is actually set from the past data.
Or previous knowledge
Or previous knowledge, experience, or whatever you have.
Yeah. So that signal to noise ratio is basically the ratio of the system.
So that I say you
variance.
can normalize in a reasonable way. But the uncertainty is really the shape of that hyperellipsoid, which is described by the covariance. And if your model is always lagging behind, then maybe some of the things you're not putting in dynamics, like cloud physics might be missing, something else might be missing.
I mean, in principle, you could consider a richer model where also the update equations are uncertain. But then they might become harder to really.
So does anybody have answer to this question as to whether Kalman was, he had anticipated, I mean, he had Bayes in his mind and he was translating the whole thing in the language of information
I
theory?
suppose he's dead.
Yes,
Yeah,
you can safely say that.
I mean, I think it's pretty clear that one can set up a Bayesian problem
Yeah.
whose answer within just applying the rules of Bayesian probability is the Kalman filter.
Yeah.
That's
Yeah,
clear.
that's been-
Whether Kalman knew this,
Yeah, that
that I have no
In
idea.
fact, the development of the Bayesian.
No, I thought somebody might know the historical.
The Bayesian dynamic model people always use the Kalman filter as part of their conceptual framework.
Well, I showed that there are very strong correspondence.
But the other way around, I don't think happened.
Yeah, I think it was after he published his paper, and then I think it was reformulated and it was shown to be equivalent to computing the posterior, probability distribution as basically.
The only thing is hard to believe that Kalman was completely unaware of
Yeah,
it.
maybe he knew it was just a.
Yeah.
It'd be good to read the paper.
Do you have an answer for the Julia?
This question, zero-level question. Why is it called a filter? What is being filtered over here?
Well, filter is, I think a term which transforms one variable into another. There's a transfer function or something like that.
Yeah, I think originally the inspiration was there's a Wiener filter, which was
Yeah.
published before the Kalman filter, and I think Kalman was extending that to the.
This is the vocabulary of linear operators.
Yeah, and so I think it sort of came from this whole idea of the filtering is the idea that there's a noisy signal embedded in your, there's a hidden signal embedded in a noisy input, and so you're trying to filter out the noise and get at the hidden signal. Yeah.
So it is really a transformer.
That's something better.
Yeah, that's the additive loss given white noise you're adding to the